Okay, so with limiting reactant, you have to kind of get an idea of what's going on here. Sorry. And when you're doing this, make sure you realize, get an idea of what's happening. We've got hydrogen and nitrogen combining together to form ammonia. And we have a reaction that says hydrogen plus nitrogen makes an H3. Now, if we balance this equation, we know that we're going to have 6 of those, 2 nitrogens, and that's balanced. So notice here in this circle, we have 3 hydrogen molecules, the light blue, and we have 1 nitrogen molecule. And what's going to happen is it's going to come over here and make 2 NH3s. And it's really important to get an idea in your head that if we had exact amounts, this is what this picture would look like. Is not at an exact amount. So notice here with the same kind of idea, what you've got going is you have 1 nitrogen and 3 hydrogens, again making 2 molecules, and you have the same situation here making 2 molecules and the same situation here making 2 molecules. But in this case, you have 2 nitrogens left over that don't have any hydrogens to react with. And so just really keep this idea in your head of what you're trying to calculate. In this case, hydrogen would be our limiting reactant, nitrogen would be our excess reactant, and we could calculate how much excess reactants left over based on the numbers here, you know, and everywhere. So keep this in mind as you're going through and doing the math, keeping the big picture in mind. So again, you could talk about this in making sandwiches. The reaction is 2 slices of bread, a piece of ham is a sandwich. So if you had this amount, what could you make? All right, so I'm just going to leave you to think about that, because if you were faced with this situation, you would know exactly how many sandwiches you can make and how many would be left over. Now what we're going to do is just apply it to chemistry, which I know sounds weird, but it's really not. It's going to be the same kind of thing. It's just not quite as nice as, you know, food. All right, so here we have a reaction where actually everything's balanced here, and we had 1 mole of this reacts with 1 mole of this to make 3 moles of this and 1 mole of this. So we're going to start really simple here. If you have 2 moles of CH4 and 2 moles of water, how many moles of H2 could you make? And do you start with moles of CH4? Do you start with moles of H2O? Because everything up to this point, you were told one thing and told to go to another thing. But now you're given 2 things. Which one do you start with? Well, it actually isn't going to matter, because you see here, it's a 1-to-1 ratio. For every 1 mole of CH4, I'm going to need 1 mole of water. So if I have 2 moles of CH4 and 2 moles of water, they both are going to limit each other. They're both going to be used up. And so it actually doesn't even matter. The limiting reactant is both of them. So I would take 2 moles of CH4, and we'd say 1 mole of CH4, because it's going to make 3 moles of H2, and this pretty much becomes what you did before. So I'm going to make 6 moles of H2. So in this case, the limiting reactant was really easy. I compared these two and I said, well, it's a 1-to-1 ratio. They're both going to run out. There won't be an excess reactant. But what if I have 2 moles of CH4 and 5 moles of water? Well, I can see here it's a 1-to-1 ratio. So if I have 2 moles of CH4 and 5 moles of water, this is going to be my limiting reactant. I only need 2 moles of water, and I have 5 moles of water. So this is, again, very clear what's going to limit me. What's going to limit me, because this is a 1-to-1 ratio, is this. That's going to be my limiting. And clearly, I'm going to have 3 moles of water left over because it's a 1-to-1 ratio. I'm going to use 2 moles of water in this reaction. So how many moles of H2 could be produced? You start with moles of the limiting reactant, because that's what's going to run out. That's going to run out. What's going to be left over is 3 moles of water just sitting there, but that's what's going to run out. And again, from the balanced equation, 1 mole of CH4 is going to make 3 moles of H2, the product, and we'll get 6 moles of H2 being produced. But here I had to decide which one is limiting. Now with a 1-to-1 ratio, super easy. We just look at it and go, well, what's 1-to-1? 2 moles of that, 2 moles of that. I'm going to have 3 moles of water left over. It's not so easy if this isn't a 1-to-1 ratio, but it's not that hard either. Now, what if we don't have a 1-to-1 ratio? Well, what we're going to have to do is say, okay, well, if this is a 1 to, say, 5 ratio right up here, well, we're just going to have to say, okay, well, only a fifth of what I need of the CH4 is going to be required for the water. So we're going to, again, look at ratios. All right, so why do we have to know if what we're giving something of the first and second reactant is limiting? Because to calculate the product, it only makes sense that you use your limiting reactant. What's going to run out first? If you have leftover stuff, that's great, but you can't make more of your product if you don't have any more of the limiting. Okay? And we're also going to be talking about the excess reactant left over. And again, just think about, well, what do I have mole to mole? So this is going to be all mole to mole. All right, so we're going to start with this. We have 2.5 moles of each reactant. How many grams can be produced? All right, well, again, this is a 1-to-1 ratio. And so grams of product, if I were to do this, I'm going to take 2.5 moles of aluminum, and it doesn't really matter because I need 2.5 moles of P as well. So these are going to run out together. I can just take 2.5 moles of aluminum. 1 mole of aluminum should make 1 mole of aluminum phosphide. And then I've got moles of aluminum phosphide, and I could change to grams. But let's try something a little more complicated. If I have 2.5 moles of aluminum and 6.2 moles of P, how much can be produced? Well, what's going to limit us? Well, because this is a 1-to-1 ratio, and this is the lower number, this is my limiting reactant. This is going to be, I have too much of this. I only need 2.5 to react with 2.5, and I have 6.2. So this is my excess reactant. I'm going to start with my limiting reactant, moles of aluminum. I'm going to say 1 mole of aluminum is going to make 1 mole of aluminum phosphide. That step is always necessary. And I will make 2.5 moles of aluminum phosphide. Now, it just says how much can be produced, and that's how much. Now, I could always switch that to grams, figuring out what does a mole of aluminum phosphide weigh. But how much of the excess reactants left over? Well, it's phosphorus. And I'm basically, no, I'm going to use that many moles of phosphorus because if I use 2.5 moles of aluminum, it's a 1-to-1 ratio. So I will use 2.5 moles of phosphorus. So I just subtract that. This is moles of phosphorus left over. Okay, so now we're going to try it with numbers. Not a huge deal though. It's 1 nitrogen to 3 hydrogens. So I'm going to go ahead and start with grams, but again, I'm going to assume that we're okay converting that to moles. So I would start by taking this many grams of nitrogen and just getting it to moles because we need to be in the mole. We need to be in the mole world. Sorry, 28 grams. So we're talking about 89 moles. Okay, so I'm going to use that, but erase it right now. I just wanted to show you that, of course, just going from Gramville to Moleville. All right, so I'm going to take 89 moles of nitrogen. Now I have 500 grams of hydrogen, so I go 500 grams of hydrogen. 1 mole of hydrogen is 2 grams, 250 moles. Okay, so now I have 250 moles. Now, I have to decide what is going to be, oops, I want to do that. What is going to be, oh my goodness. Okay, that's just not erasing, and I don't understand why, but that's all right. We'll just ignore it. So I have to decide between these two what is limiting. Now, it's not as easy because it's a 1-to-3 ratio, but all I'm going to do is I'm going to take the 89 moles of nitrogen, and I'm going to look, a 1-to-3 ratio is what is needed. So I am going to need actually 268 moles of hydrogen. That's what I'm going to need. If there's a 1-to-3 ratio here, yes, it gets a little bit more complicated. It's not just 89 to 89. It's 1-to-3. So I'm going to say, okay, well, I'm actually going to need 268 moles of hydrogen. So to run this reaction to completion, I need 89 moles of this, and I need 268 moles of that. And between the two then, they would both run out at the same time, and I'd make all the product. In this case, though, I don't have the 268 moles that I need of the hydrogen. I only have 250 moles. And I would need 268 moles to run this to completion. So this is my limiting reactant. This is going to run out first. And there's going to be a little bit of extra nitrogen here. So what I'm going to do is I'm going to take the 250 moles, what I have of the hydrogen. I'm going to say 3 moles of hydrogen will make 2 moles of NH3. So 250 times 2 divided by 3, and I should make 167 moles of NH3. That's how much should be produced. Now, you could always go back and say, well, how much of this is left over? And that's another question we should tackle. And if you look at this as a ratio of 3 to 1, now I started with 89 moles of nitrogen. I needed 268. I didn't have it. All I had was 250. That was my limiting. I used my limiting to find my product. That only makes sense. That's the thing that's going to run out first. There'll be leftover nitrogen here. We can always figure out how much nitrogen's left over, and we could do that by taking this right here, this 250 moles of hydrogen, doing a 3 to 1 ratio to it, and finding out what was really used. We'd go 250 moles of hydrogen. That's what's used up. Visualize the tank. It was a 3 to 1, 3 moles of hydrogen to 1 mole. So what we actually have left used up is 83 moles of nitrogen. So this was what was really actually used up. I started with 89, used up 83. We have 6 moles of nitrogen left over. So just listen to this over and over again. All right, so we'll just do one really quickly here. Figure out what's our limiting. So again, I'm going to take the 120 grams of Cl2. I'm going to get it 2 moles, and then I'll probably just erase this to get rid of it. And I have 1.69 moles of chlorine. All right, Cl2 weighs. So I have 1.69 moles of chlorine. All right, so I'm going to kind of keep that in mind. Chlorine is going to be 1.69. In the same sense, I'm going to take that 750 grams of Ki, and I'm going to take the K, which is 39, and the I, which is 127. And basically, I'm going to go 750 divided by 166, and that gives me 4.52 moles of Ki. So I just converted these. All right, it's a 1 to 2 relationship. If this were a 1 to 1 relationship, I'd say, oh, this is limiting right here. But it's a 1 to 2, which makes it a little bit more confusing. So I'm going to take 1.69 moles of Cl2. 1 mole of Cl2 will require 2 moles of Ki. So I actually am going to need 3.38 moles of Ki to react with it. Now, I'm going to need that, but I have 4.52. So compare these two. I have 4.52. I only need 3.38 moles to react with it. So I actually have more than I need. This is my excess reactant. This is my limiting. That's what's going to run out first. So I'm going to use my limiting and say 1 mole of chlorine is going to, it says each reactant, but let's just do I2. We'll make 1 mole of I2. I should be able to make 1.6 moles of I2. Now I can always get that back to grams if I want to, but that's what I should be able to make. Now as far as the excess reactant left over, it's pretty easy. I'm going to take 4.52 moles, that's what I had to start with, of Ki. I'm going to subtract 3.38 moles of Ki, that's what was needed and used up by the limiting. Remember, it's always the limiting that determines everything, right? Because it runs out first. And so we should be left with 1.14 moles of Ki left over. Now, again, you can get that to grams if you need to. You just need to practice this a lot. I'll just quickly do percent yield. Percent yield, all our calculations are just theoretical. It's how much it get if everything, goes right, but there's always side reactions. It could be soluble in the medium. The reaction doesn't go to completion. Many things. Nothing is usually 100% yield. All right, all we're going to do is take actual yield. This is what you actually are going to get in the lab. That's what you weigh in the lab. this is what you calculate, which I guess it says right beneath here, what you calculate, okay? And time. So percent yield, the precipitate should be 34 grams after doing all the calculations, whether it's limiting reactant, whatever, some stoichiometry, but in the lab, only getting 22. So we just take what we get in the lab, divide it by theoretically what we should get in our calculations. This is our stoichiometry, and that is going to be our percent yield times 100, so 64.9%.
Hello?